In 1858, Queen Victoria sent the first telegram ever to cross the Atlantic Ocean. 99 words, from Ireland to Newfoundland, carried beneath 2,000 miles of open ocean by a copper wire wrapped in nothing more than the hardened sap of a tropical tree. It took 16 hours to transmit, and when the news reached the public, the reaction was unlike anything the modern world had ever seen. New York erupted. Church bells rang for hours. Thousands paraded through the streets carrying torches and banners. Fireworks launched from the roof of City Hall, and the sparks caught the dome on fire. One of America's most iconic government buildings was literally burning above the crowd, and nobody stopped celebrating. Newspapers across the Western world called it the single greatest achievement in human history. For the first time, a message could cross the Atlantic without spending 2 weeks on a ship. 2 continents, linked by a pulse of electricity. Instant global communication had arrived. 3 weeks later, the cable went dead, permanently. Over $1 million, about $35 million today, and years of effort reduced to a lifeless rope on the ocean floor. Not by a storm, not by sabotage, not by anything natural. It was one man, a surgeon-turned-electrician who ignored the explicit warnings of one of the greatest physicists alive, hooked up massive electrical coils to the line, and forced thousands of volts through insulation. That was never designed to survive it. He burned the cable alive, and this is the story of how he did it. To understand why this one cable mattered so much, you need to picture what communication actually looked like in 1858. If you were sitting in London and needed to get a message to New York, your options were simple. You wrote a letter, you carried it to the docks, you handed it to someone on a steamship, and then you waited 10 days if the weather cooperated. 3 weeks if it didn't. Think about what that means. A financial crisis could erupt in London, and Wall Street wouldn't know for 2 weeks. A war could break out on one continent, and the other wouldn't hear about it until the fighting was already old news. Telegraph lines had already transformed communication on land. London to Edinburgh in minutes, New York to Philadelphia in seconds. But all of that stopped at the coastline. The Atlantic Ocean was a wall, 2,000 miles of deep, freezing, pitch-black water that no cable had ever crossed. Cyrus Westfield looked at that wall and decided to tear it down. Now, here's the thing about Field. He wasn't an engineer. He wasn't a physicist. He was a 34-year-old retired paper merchant from Massachusetts who'd made a fortune young and was restless, ambitious, and completely ignorant of electrical science. That combination was going to make him either a visionary or a fool. History would take 8 years to decide which. In 1854, a British engineer named Frederick Gisborne came to Field with a modest idea: run a telegraph line from Newfoundland to New York. Field looked at the map, looked at the ocean, and asked the question that would consume the next decade of his life. Why stop at Newfoundland? Why not go all the way to Ireland? He pulled together a syndicate of New York's wealthiest men, Peter Cooper, Moses Taylor, Abram Hewitt, and founded the Atlantic Telegraph Company in 1856. They raised £350,000 in shareholder capital, contracted 2 of Britain's largest cable manufacturers, and persuaded the Royal Navy and the U.S. Navy to lend warships for the crossing. The engineering challenge was staggering. They needed over 2,000 miles of cable, strong enough to survive depths of 3 miles, flexible enough to drape over underwater mountain ranges, and insulated so thoroughly that electrical signals could travel the full distance while surrounded by millions of tons of conductive salt water under crushing pressure. Everything came down to one question: what do you wrap around the copper to keep the ocean out? There was exactly one material on the planet that could do the job. It came from the jungles of Southeast Asia. But the real danger wasn't the ocean. The real danger was already inside the wire. Deep in the rainforests of the Malay Peninsula grows a tree called Palaquium gutta. slice into its bark, and it bleeds a thick, milky sap that hardens as it cools into a gray, rubbery substance. The Victorians called it Gutta-Percha, and in the 1850s, it was the closest thing to a miracle material that existed. Imagine a material that does everything you need: waterproof, salt-resistant, moldable under heat, and critically, an excellent electrical insulator. Rubber dissolved in seawater within months. Gutta-Percha could last years. It was the only substance on Earth that made undersea telegraphy possible. There was just one problem, and it was invisible. The manufacturing technology of the 1850s could not apply gutta-percha flawlessly. Every layer contained microscopic air bubbles, tiny voids trapped during the molding process. The boundary between copper and coating was never perfectly smooth. There were always weak points that no inspection tool of the era could detect. At low voltage, these defects were harmless. Under extreme electrical stress, they would become catastrophic. But nobody knew that yet. The Gutta-Percha Company of London wrapped 3 layers of insulation around a core of 7 copper wires twisted together, each thinner than a sewing needle. Then 2 separate firms armored the cable with iron wire and created another problem nobody caught. Glass, Elliott & Co. wound their half-clockwise. R.S. Newall & Co. wound theirs counterclockwise. When the 2 halves met in the mid-Atlantic, the opposing spirals fought each other at the splice point like 2 ropes being twisted in opposite directions. The cable was compromised before it ever touched the water. The first attempt to lay it, in August 1857, ended when a wave snapped the cable 6 days in. Nearly 400 miles of wire sank 3,000 meters to the ocean floor. Irretrievable. They tried again the next summer. Both ships would meet mid-Atlantic, splice the cable, and sail in opposite directions. Several more attempts failed. More storms, more breaks. Finally, on August 5, 1858, both ships reached their shores. The Atlantic had been bridged, and for a brief, remarkable moment, it worked. Messages crawled across the ocean floor. Slowly, painfully slowly. But they crossed. All the cable needed now was careful, patient handling. What it got instead was a man with a 5-foot induction coil and a theory that would have horrified every physicist in Europe. While the world was celebrating, one man on the company's board had been running the numbers, and the numbers were terrifying. William Thomson, later known as Lord Kelvin, was one of the finest physicists alive. He understood what almost nobody else grasped. A submarine cable this long doesn't behave like a telegraph wire between 2 cities. It behaves like a capacitor. It absorbs pulses and smears them into slow, muddy waves, double the length, quadruple the distortion. Thomson's solution was the opposite of brute force. Send tiny signals, a few volts, and build a receiver sensitive enough to read them. He invented the mirror galvanometer, a magnet the size of a grain of rice suspended from a silk thread inside a copper coil. When the faintest current passed through, it tilted a mirror no bigger than a fingernail. A beam of light bounced off that mirror onto a scale across the room, invisible electrical whispers translated into readable light. Thomson didn't need power, he needed precision. The man who held the keys to the station saw things very differently. Edward Orange Wildman Whitehouse was not a physicist. He was a surgeon who'd wandered into electrical experimentation with enthusiasm, some talent, and no formal training in the underlying science. He didn't understand capacitance or signal propagation. What he understood was simple. The signal was weak, so he would make it stronger. More voltage, more power. At the Valentia Island Station in Ireland, Whitehouse installed enormous induction coils, early transformers the size of furniture. These machines could multiply voltage enormously, generating pulses of up to 2,000 volts. For context, Thomson's galvanometer worked on a few volts. The Gutta-Percha insulation was designed to handle maybe tens of volts under normal conditions. Thomson warned him, directly, explicitly. High voltage will destroy the insulation. The physics is not negotiable. Whitehouse dismissed him. And here's what nobody wants to admit. Whitehouse wasn't stupid. He was confident. He had hands-on experience. He had the board's trust. He was everything we're taught to value in a leader: decisive, experienced, self-assured, and he was catastrophically, irreversibly wrong. He threw the switch. 2,000 volts tore through the copper core and radiated outward into the Gutta-Percha. Every microscopic void became a point of catastrophe. The air inside each bubble ionized and sparked. This is dielectric breakdown. The moment an insulator becomes a conductor, each spark superheated the surrounding Gutta-Percha, turning insulation into carbon. Carbon conducts. So where there had been an insulating void, there was now a conductive scar. The next pulse found that scar and extended it. Engineers would later call this electrical treeing because the branching paths of carbonized insulation spread like roots through soil. Day by day, the signals dimmed. Messages arrived as garbled noise. Whitehouse increased the voltage. By September, the cable was failing. By October, it was silent. The Gutta-Percha had been incinerated from within, and the Atlantic had claimed the copper core. 732 messages. That's all the first transatlantic cable ever carried. The aftermath was swift. The Atlantic Telegraph Company convened a formal investigation. The Board of Trade Inquiry of 1861 confirmed what the physics had already demonstrated. Wildman Whitehouse bore the primary responsibility. He was dismissed. His name became a footnote, a cautionary tale. He vanished into historical obscurity, remembered only as the man who electrocuted the first global communications network. Cyrus Field watched his investors' fortunes disappear into the Atlantic. Over $1 million, roughly $35 million in today's money, gone. Not gradually, not through decline, gone. The financial world's confidence in transatlantic telegraphy evaporated overnight, and the world went dark. Without the cable, communication between the continents snapped back to the speed of canvas and wood. A steamship, 10 days to cross. During the most volatile decade of the 19th century, as the American Civil War ripped the United States apart, as Italian unification redrew the borders of Europe, the two halves of the Western world went deaf to each other. The blackout lasted 8 years. Field refused to quit. By 1865, he'd raised fresh capital, commissioned a vastly improved cable, and chartered the one ship on the planet large enough to carry the entire thing, Isambard Kingdom Brunel's enormous SS Great Eastern. No more splitting the cable between two vessels, no more risky splices in the mid-Atlantic. One ship, one cable, one shot. It still went wrong. In August 1865, just days from reaching Newfoundland, the cable snapped, 2,000 fathoms below the surface. The crew spent days trying to grapple it. They couldn't reach it. It would take 3 more attempts, one colossal ship, and the total rejection of everything Whitehouse believed before the Atlantic would carry a signal again. On July 13, 1866, the Great Eastern departed Ireland for the last time. Everything had changed. 4 layers of Gutta-Percha instead of 3, with adhesive compound sealing each layer. Tighter manufacturing tolerances, fewer voids, fewer bubbles, heavier armoring, wound consistently in one direction, and most importantly, Thomson's philosophy. Low voltage, the mirror galvanometer, precision over power. On July 27th, the cable landed at Heart's Content, Newfoundland, and then the Great Eastern did something remarkable. She turned around, sailed back to the exact coordinates where the 1865 cable had broken, grappled it from the ocean floor, spliced it to new cable, and completed it. By the end of 1866, 2 transatlantic cables were operational. The lesson had been paid for, in the most expensive way imaginable. There is a temptation to tell this story as a clean morality tale. Smart scientist warns reckless amateur. Amateur ignores warning. System collapses. The end. But that misses the real lesson. Because Whitehouse's failure wasn't really about voltage. It was about a way of thinking. When Whitehouse looked at a weak signal, he saw a power problem. His logic felt intuitive, even reasonable. If you can't hear someone across a noisy room, they should speak louder. So he built a bigger speaker. But a 2,000-mile submarine cable isn't a room. It's a system governed by absolute physical limits. Gutta-Percha can insulate up to a certain voltage, not a volt more. No amount of ambition or confidence or institutional authority changes that number. The material doesn't negotiate. Thomson looked at the same weak signal and asked a completely different question. What if the problem isn't the signal, but our ability to hear it? Instead of building a louder transmitter, he built a quieter receiver. His mirror galvanometer didn't demand anything from the cable beyond what its physical structure could deliver. It just listened more carefully. The most dangerous person in any engineering project isn't the one who knows nothing. It's the one who knows enough to be trusted, but not enough to understand where their knowledge ends. Whitehouse had experience, he had authority, he had conviction, he confused all three for understanding. And this isn't ancient history. In 2013, divers off the coast of Alexandria, Egypt severed 3 submarine fiber optic cables in a single incident, and internet speeds across an entire region collapsed. The physical infrastructure carrying the modern world's data is not as different from 1858 as we'd like to believe. The pattern Whitehouse embodied repeats in every era. The operator who pushes a system past its rated limit because nothing broke yesterday. The executive who dismisses a technical warning because the timeline doesn't allow for caution. The confident generalist who overrules the quiet specialist. The Gutta-Percha didn't care about Whitehouse's confidence. It cared about voltage. And when the voltage exceeded what its molecular bonds could hold, it did exactly what the laws of physics demanded. It broke. The first transatlantic cable wasn't destroyed by immature technology. It was destroyed by a man who refused to respect what the technology could and could not do. Right now, at this very moment, the floor of the world's oceans is threaded with more than 500 submarine cables stretching 1.7 million kilometers. 99% of all international internet traffic, every email, every video call, every bank transfer, every message that crosses a border doesn't travel through satellites. It travels through glass fibers thinner than a human hair, resting on the seabed. Modern submarine cables are incomparably more advanced than anything built in 1858, but they are still physical objects in a hostile environment with physical limits. Around 200 breaks still occur every year, ship anchors, fishing trawlers, earthquakes, and the diameter of a modern cable is roughly the width of a garden hose, not much larger than the wire Whitehouse destroyed. The lesson from 1858 hasn't expired. The infrastructure connecting the modern world is not invulnerable. It is not abstract. It is not floating in any cloud. It is a real, physical thing, made of real materials, lying on the floor of a real ocean. It works only because engineers eventually learn to respect what those materials can and cannot withstand. Thomson didn't save global communication by building a more powerful machine. He saved it by building a more sensitive one. He didn't shout louder across the ocean. He learned to listen. That shift from force to precision, from arrogance to humility, is the reason you received this signal today. If the hidden physics and logistics behind the systems that shaped our world are the kind of thing that keeps you thinking, consider subscribing. There are a lot more stories buried in the infrastructure we all take for granted.